Once again, welcome everyone, and thank you for joining us for this IT Learning Hub webinar, Pedestrian Safety, Travel Monitoring, and Relating the Two. This webinar is being presented as part of a series partnership with the National Travel Monitoring Exposition and Conference, or NATMEC. NATMEC was created to provide travel monitoring professionals and transportation data users from around the world opportunities, share knowledge and good practices, exchange ideas, revisit fundamental concepts, learn new processes, procedures, and techniques, and see the latest advancements in policy, technology, and equipment. Pedestrian injuries and fatalities have increased in both number and share in recent years, nationally and in many states. There is a need for improved pedestrian crash prediction, but methods to better understand factors associated with pedestrian safety, and also to assist in the prioritization and selection of countermeasures to improve pedestrian safety at signalized intersections. Pedestrian exposure data is one of the biggest barriers to overcome for pedestrian safety analysis. Learn about the 3 different approaches used to improve pedestrian safety through better estimation tools. 2 presentations today will focus on efforts that use pedestrian push-button data at signalized intersections. One project uses these novel data to improve crash prediction models to test the safety and numbers concept that's been demonstrated with bicycling. Another uses these data through a machine learning approach to create typologies of pedestrian activity patterns to better convert short-term counts to annual volumes. The 3rd presentation shares a new method developed for identifying and prioritizing additional count locations to aid cities or states seeking to grow their count data collection programs. And the learning objectives for today's webinar are to understand how push-button data as a measure of exposure can be used to predict pedestrian safety at signalized intersections, appreciate distinctive typologies of pedestrian activity that could be used as factor groups to explore short duration counts to daily, weekly, and annual volume estimates, and recognize how travel monitoring through an iterative process of model estimation and count location identification can be pursued to continuously refine an agency's pedestrian exposure estimates. I would now like to introduce the presenters for today's webinar. Abdul Islam is a graduate assistant for Utah State University. Prasanna Humajan is a graduate research assistant for Utah State University. And Brian Almdale is a planner for tool design. And today's Q&A moderator will be Sarah Worth O'Brien, Senior Research Associate at UNC Highway Safety Research Center. And at this time, I would like to pass things to our first presenter, Abdul.
Thanks, Boom, for giving me the floor. I cordially thank Dr. Maker and Dr. Singleton for nominating me as the presenter in the NATMEC webinar. I'm going to talk about my research on safety in numbers, developing improved safety predictive methods for pedestrian crashes at signalized intersections in Utah using push-button-based measures of exposure. In the US, according to National Highway Traffic Safety Administration, there were nearly 6,300 pedestrian fatalities in 2018. This number was an increase from 4,100 in 2009 and was higher than in any other year since 1990. That makes 2018 the deadliest year for pedestrians in US. Utah is not immune to this issue and has also seen increases in the number and rates of pedestrian fatalities and injuries over the last 10 years. In 2016, nearly 40 deaths and 900 injuries to people walking on Utah streets and highways were reported. Considering per year fatalities of pedestrians and motor users, we observed a decreasing trend in the in death of vehicle occupants and an uptrend in death of people walking on streets. This scenario initiates an increased need for improved pedestrian crash prediction methods to understand factors affecting pedestrian safety and prioritize safety countermeasures. Typically, the biggest barrier to overcome for pedestrian safety analysis is the lack of more robust data on pedestrian exposure. We are using pedestrian volumes from push-button based measure of exposure as our exposure. A secondary motivation for this work was to examine the safety numbers hypothesis for walking. While there has been a number of researches on this topic in European context, research regarding the safety numbers concept in US is very rare. With that in mind, the focus of this study is twofold. First, to estimate models of pedestrian crash frequency and severity at signalized intersections using pedestrian and traffic volumes and other predictor variables. And second, to examine whether the safety numbers effect applies to pedestrian safety in the US using robust measures of pedestrian exposure. This concept, however, suggests that pedestrian and bicycle crash rates decrease with increasing volumes of people walking and bicycling. This is the outline of the presentation. There are as many as 2,500 traffic signals or hawks all over Utah. Out of these, 1,500 are connected with pedestrian push-button data. Our model includes data from 919 signalized intersections due to lack of data on traffic volumes, speed, and road geometries at some intersections. We also excluded flasher and hawks due to their slight complex nature during analysis. Google Earth and Street View were extensively used for the collection of road geometry data. For example, information of no right turn on red, channelized right turn, crosswalk distance, type, and bus or bike lanes were collected from Google Earth and Street View. The dataset also included information on sociodemographic, which we collected from US Census. Land use data we assembled from Utah AGRC website, and exposure, speed, and other information regarding vehicle or crashes were collected from Utah Department of Transportation. As a measure of pedestrian exposure, we used pedestrian push-button data. This data collection effort was actually done as part of another research project. However, I can give an overview of that research. Every time a pedestrian push button is pressed in the state of Utah, this activity is recorded and UDOT archives this traffic signal pedestrian actuation data for use in its automated traffic signal performance measure, in short ATSPM system. Figure shows the ATSPM system architecture. Event code 45 is logged when a call to service for a particular phase is registered from pedestrian demand. Event code 90 is logged each time when multiple pedestrians pushes the button in a single cycle of crossing. The pedestrian crossing events were manually counted from video recording for 90 signals and 320 crosswalks in Utah for more than 22,000 crossing hours of video at all hours, all weekends, all weekdays, and all seasons. They counted more than 175,000 pedestrians in the process. Then the data were modeled from where we got the hourly pedestrian crossing volumes with pedestrian calls as predictors. Later, the data were segmented according to facing time, pedestrian activity level, and cycle length. Overall, the model showed good fitting results. The figure here shows pedestrian crossing volume at signals with numbers of events logged. Based on the result of that project, we applied the estimated model over the time period of 1 year from July 2017 to June 2018 to extract annual average daily pedestrians volume, which we call AADP. You can see the descriptive statistics and histogram of the pedestrian exposure data here. Next, we collected data involving pedestrian crashes that occurred in Utah for 10 years time period from UDOT Numetric website. Use of zero inflated negative binomial model best suited for the pedestrian crash frequency analysis, as the data were over dispersed and more than half of the study intersections had zero pedestrian crashes. Figure shows the distribution of pedestrian crash frequency. Ordered logit model was selected for the pedestrian crash severity analysis due to the ordinal nature of the pedestrian crash severity levels. We categorized about 2,500 pedestrian crashes over the 10 years time period into 5 injury severity levels. Almost half of the pedestrians involved in crashes, about 44%, were minorly injured, and 13% of them were seriously injured. The percentage of fatal crashes, however, was 2%. The results from zero inflated model developed for crash frequency analysis suggested that both pedestrian volume and traffic volume were significantly associated with crashes. An increase in vehicle volumes by 1% increased the number of pedestrian crashes by 0.31%. Among the road network characteristics, intersections with greater crosswalk distance had slightly more pedestrian crashes. A 1-foot increase in mean crosswalk distance was associated with a 0.6% increase in crash frequency. Also, intersections with more far-side bus stops saw more pedestrian crashes, as did the intersection with more nearby transit stops, and those with more marked crosswalks. Among the built environment characteristics, pedestrian crashes were more frequent in areas with larger shares of residential and of commercial land users. While considering socio-demographic characteristics, household size showed a positive association, but median household income showed a negative association with the frequency of pedestrian crashes at study sites. From the crash severity analysis, several crash characteristics relating to the vehicle and driver had association with severity. Pedestrian crashes were more severe when they involved large or even medium-sized vehicles compared to smaller vehicles. Many of these vehicles have higher hoods and centers of gravity, and thus are more likely to run over a pedestrian rather than throwing them over the hood, as is the case with small passenger cars when a collision occurs. Speed is a significant risk factor for more severe pedestrian crashes due to the greater transfer of energy. This is also reflected in the reduced injury severity for left turning and especially right turning vehicles, which tend to operate more slowly than through moving vehicles. Our model result also implied that a doubling in pedestrian crossing volumes would be predicted to increase crash frequency by only 12%, which proves the safety in numbers concept. The figure here depicts this relationship where pedestrian crash rates decline with increasing pedestrian volumes. Although our analysis was not designed to uncover the reasons for the safety in numbers relationship, potential explanations as in that more often motorists see people walking, the more likely they are aware of them and the more experience they have driving safely around non-motorized users. This finding supported multifaceted efforts to increase walking and promote pedestrian activity in cities and communities. Our findings also support efforts to reduce vehicle turning speeds through intersections geometries and to provide context-specific speed limits, especially in high pedestrian volume areas. We recommend shortening of crossing distance by curb extension, which also promotes signal timing efficiencies. The positive association between residential or commercial land users and pedestrian crashes support efforts to focus on pedestrian safety in those areas. More importantly, the negative association with median household income is troubling from an equity perspective, as it suggests that lower income neighborhoods experience a disproportionately greater burden of pedestrian crashes. Finally, the significant positive link between driving under influence, drowsy and distracted driving and crash severity further highlights the importance of education and enforcement efforts to reduce this unsafe driver behavior. We acknowledge the contribution of UDOT and its members who were directly involved with the research project. Their guidance and feedback were useful. We'd also like to thank students of Utah State University who helped to assemble some of the intersection data. Here are our contacts in case you need us. Thank you for your patience.
Thank you, Abdul. We will now move on to our next presentation. Prasanna, you may go ahead.
Thanks, Karim. Hello, everyone. I'm Prasanna Humagai, a PhD candidate at Utah State University. First of all, I would like to thank NatMec and ITE for organizing this webinar and allowing me to present my research on the topic, develop typologies or factor groups of pedestrian activity patterns at signalized intersections using pedestrian push-button data. This work was done in collaboration with my supervisor, Assistant Professor Dr. Patrick Singleton. So in the following presentation, I'm going to start off with introduction to existing pedestrian data collection methods, objectives of the study, and then move on to the methodology and how we were able to form typologies based on clustering, the impact of built environment characteristics, and finally conclude with the key findings and work to be done in the future. So existing methods for counting pedestrian activity at intersections can be classified into manual and instrumented or automatic approaches. Manual counts involve collecting pedestrian volume in real time or later using video recording. However, they are time consuming and infeasible over long time periods. The other approach includes use of technology-based counting methods like microwave, infrared, inductive loops, etc. However, they require higher upfront costs and are infeasible across multiple locations. Hence, the main idea behind this project was to explore an alternative way of collecting long-term pedestrian data across multiple locations, which is by using the pedestrian push-button data. There are two main objectives of this study. The first is to develop pedestrian activity metrics from data available from Automated Traffic Signal Performance Measure System, also called ATSPM. And the second objective is to develop approaches for determining typologies of those signalized intersections based on the developed pedestrian metrics. So pedestrian locations are often grouped together according to their activity patterns, let's say daily or weekly or yearly, and these groupings are called factor groups. The recent work in this field shows use of two approaches to group pedestrian activity at intersections. The first is called empirical clustering approach, where intersections with similar activity patterns are grouped together by using clustering, the principle of which is to minimize the differences in patterns across the same clusters, whereas at the same time maximizing differences in patterns with other clusters. The second approach is land use classification approach, where locations with similar activity patterns corresponding to their distinct land use characteristics are grouped together. For example, let's say an urban area or a downtown or intersection near a park, so distinct activity patterns and grouping them together is done under this approach. As already told by my friend Adul, so we used this pedestrian traffic signal activation data So once a pedestrian push button is pressed in the intersections with pedestrian push buttons at the state of Utah, the data is automatically recorded in Utah Department of Transportation's ATSPM system. So the following figure shows a sample interface of pedestrian delay at one of the intersections. So from this UDOT's ATSPM website, one can easily get the information regarding pedestrian detection or time or phase control and many other events. And this kind of data was used for this research. So the methodology of this research involved three major steps. The first, data assembly, then data processing, and then finally the clustering. So we downloaded raw traffic signal data from ATSPM for about more than 2,000 intersections for over 1 year, from July 2017 to July 2018. And we extracted pedestrian relevant event codes. Second, we developed relevant pedestrian activity metrics and prepared data processing steps in RStudio. Then for each intersection, we calculated those metrics and simultaneously we visualized the data. And the final step involved time series clustering, which will be explained in detail later in this presentation. As I said briefly in the previous slide, we extracted various pedestrian-related events such as 0 for phase on, or 21 when pedestrian begins to walk, or 23 when pedestrian begins solid or don't walk sign. However, for this study, we used pedestrian detections and pedestrian calls registered. So whenever a push button is pressed, a pedestrian detection is recorded. However, the pedestrian call registered, or 45, only occurs once per phase when a call to service for pedestrian phase is made. We can see this from a small animation here. So once a, So once a pedestrian push button is pressed, the call is registered. But if the push button is pressed multiple times, only the detections will get registered, but not the calls. So we developed this pedestrian activity matrix based on number of pedestrian detections and calls registered. But we also use several variations, that is number of detections per phase, and also as a proportion of those pedestrian detections within a week. However, each of these metrics were calculated per hour in a week, averaged over 1 year. That is, we used a normalized count. The objective behind averaging across the whole year was to nullify some of the effects of temporal variation caused by special events, festivals, and other unusual activities. So one example of these pedestrian activity metrics, that is number of pedestrian calls registered per hour, or 45s per hour, is shown here. So as you can see, there is a distinct midday peak over here, and the pedestrian activity is consistently higher and about more than 20 pedestrian call registered per hour. So after calculating the pedestrian activity metrics for each measures, we then proceeded with clustering. So only 1,522 signalized intersections remained after removing incomplete data. The first step in clustering is to select a dissimilatory measure. Shape-based dissimilatory measures such as Euclidean distance allowed us to compare magnitude of pedestrian activity across those intersections, whereas structure-based dissimilatory measures such as chord or dynamic wavelet transform help us to compare time series based on their patterns or simultaneity of patterns. Similarly, we used K-means algorithm, which works on minimizing the within cluster sum of squares. After forming those clusters, we use some statistics to determine efficiency of clustering. The efficiency of clustering is given by distinctiveness and compactness within each clusters. So we used within sum of squares, average distance within the cluster, average silhouette width, and done index in our analysis. So this slide is about how we determine dissimilarity index, how we determined which pedestrian activity metrics to use, and how did we determine the number of clusters. First, we should know that clustering method is an iterative process. So to determine the number of clusters, we varied the number of clusters from 2 to 7 using various dissimilarity measures, but 3 clusters were deemed best based on their distinctness and compactness, both using the validation statistics and using the visualization. Similarly, for choosing the magnitude-based clusters, Euclidean distance and 45s per hour or calls register per hour were found best. We also tried to include 90s per hour and 45s per hour for phase, but they showed very high disturbances. For example, in the figure you can see using 3 number of clusters and 45s per hour, we were able to form 3 distinct clusters: high volume, low volume, and high volume given by green, medium volume by red, and low volume by black. Similarly, for identifying patterns within the intersections, we used CORT, or temporal correlation, and 3 number of clusters, and using CORT showed similar distinctions as shown in the figure here. Now moving into the cluster results, as explained before, 3 clusters were formed based on the magnitude, that is high, medium, and low, and 3 based on their patterns, like single peak, double peak A, and double peak B. Cross classification between these 2 clusters gave us 7 unique typologies, defined by their magnitude and their shape of patterns. Now we describe each typologies and their characteristics. In the figure, the x-axis shows hour of the day in a week, whereas the y-axis shows number of pedestrian calls registered per hour, and the same expressed as proportion of weekly proportions 45s per hour. So there were altogether 32 intersections belonging to type 1. Note that the figure or the pattern here shows the average across all the intersections which belong to this typology. So as you see in the figure, intersections belonging to this typology tend to maintain consistent high level of pedestrian activity throughout the day and the week, and are marked with high midday pedestrian activity, about more than 75 calls registered per hour. But the peak hours consisted of only 1% of total weekly activity, which is normal because of the high pedestrian activity distributed all over the week. The second category is the medium volume ones, which show lower pedestrian activity than the high volume ones, that is less than 50 calls registered per hour. In the first type, type second, which looks similar to the high volume ones, there were 164 intersections, and they showed moderate midday activity, about just greater than 30 calls registered per hour. The other type, type 3, consisted of 12 intersections, but they have different shape than the previous ones. They have clear 2 peaks, where PM peaks are larger than the AM peaks, and also the peak weekday hours consisted of more than 3% of the total weekly activity, about 3%. The other category in this medium volume is the type 4, where only 12 intersections were present, and this also shows larger PM peaks, but uniform pedestrian activity from AM to PM. And the peak weekday hours also constituted of about 2% of total weekly activity. Moving on to the third, the low volume ones, they show only very low low pedestrian activity, around less than 10 calls registered per hour. So the type 5 looks similar to the previous medium and high volume ones. So most of the intersections, around more than 50% of the intersections were in this category, which showed less than 10 pedestrian calls per hour, whereas the peak hours were about 1% of the total weekly volume. Type 6, there were like 250 intersections, which showed similar to the medium volume ones, clear AM and PM peaks, with PM peaks being greater than the AM peaks, whereas the peak hours consisted of around 2 to 3% of total weekly activity. The last one, the type 7, there were 185 intersections in this typology, and higher PM peak activity was shown here as well, but the only difference between type 6 and type 7 was how they constituted the total weekly volume, just about 2%, rather than 2 to 3% in the type 6. So we all know that pedestrian demand is influenced by land use characteristics, employment generators, and other density factors. Hence, we calculated population density, household density, employment accessibility, number of transits and schools around the intersections for each typology. So for this purpose, we first created a buffer of about 0.5 miles around each signalized intersections, and we calculated all these attributes by area weighted average for the census block groups within 0.5 miles of this intersection. We used the data from UDOT and other land use characteristics from the same state government sites. So results averaged across all signals in each typology shows that the main important factors that affects the magnitude as well as the peaking patterns of this typology was residential density and job accessibility. Overall, the key findings from this study was that pedestrian calls registered was a suitable pedestrian activity metric to define the typologies. However, we find that there is a need to refine these metrics and choose the one that has high correlation with the observed counts, as already said by Adu in the previous presentation, that we collected a number of video data, so we are refining those metrics and trying to use the one which is best which can best transform to the actual pedestrian counts. Similarly, Euclidean distance and court were the two discriminatory indexes we found more favorable than others, and in the future we are also trying to include other attributes such as phase and pedestrian recall into our clustering. And we also find that areas near downtown or intersections near downtown and near school and parks were found to be attracting more pedestrians than other areas and were having consistently high pedestrian activity. Moving on to our center part, that there are more works remaining. First, instead of doing clustering on both magnitude as well as pattern, we are trying to find the intersections with similar patterns only so that we can use the manual counts and form the expansion factors. So our second work is to compute hourly, daily, weekly, and monthly expansion factors. And one way of doing it is shown in the figure where we describe hourly proportion of average daily volume across three different typologies. One, the high volume one, shows uniform pattern, whereas there is more of a clear AM and PM peaks around the other medium and low volume, and these are bound to affect the expansion factors, as each hour will have different expansion factors. And the remaining work is also to compute different built environment characteristics around the intersections, and at last we're planning to relate those intersections and our clustering work so that we can use that in the other intersections or in out of sample data or in those intersections which are not signalized intersections right now. So this project was funded by Utah Department of Transportation, and we want to thank Utah Department of Transportation as well as the members of other technical advisory committee for their feedback on this work. If you have any questions, you can contact us through our email or through our contact number. Thank you. I'll pass this to Kelly now.
Thank you, Prasanna. We will now move on to Brian's presentation.
Hi everyone,
Thanks for attending this webinar. My name is Brian Allendale. I'm a planner at Tool Design, and I'll be discussing methods used to estimate pedestrian volumes across a citywide network, as well as the development of an algorithm used to prioritize future pedestrian count locations to enhance agency count programs and to advance traffic safety goals. The content I'll be discussing in this presentation is part of the published second phase of the Seattle Bicycle and Pedestrian Safety Analysis Project, the BPSA, which updated network screening tools for the Seattle Department of Transportation to identify high-risk locations for bicycle and pedestrian crashes. This process requires developing an understanding of activity patterns for both modes based primarily on volume and count data. This presentation will cover both bicycle and pedestrian topics, as both modes share some similarities related to volume estimations and safety analysis, though I have excluded many of the bicycle components. I'd like to give some special thanks to Chris Stavopoulos and the Seattle Department of Transportation, Rebecca Sanders, and Michael Hintz for their roles in collaboration in the development of both phases of the BPSA. To set the stage, bicycle and pedestrian count programs are not nearly as robust as motor vehicle count programs. Motor vehicle count programs on the left typically have an institutionalized process in which permanent counters with well-established patterns and extensive short-duration count coverage allow for motor vehicle AADT along almost every street. Whereas with bike and pedestrian count programs on the right, there are very few permanent count locations and a small number of targeted short-duration counts, which requires a handful of statistical modeling to be able to estimate bicycle and pedestrian AADT. Looking at these two types of count programs, just comparing them visually, it's clear that they're pretty different. So how do we improve pedestrian and bicyclist count data collection and volume estimation? There are a few ways. Today we'll discuss two elements from the BPSA Phase 2 that have been used by the City of Seattle and can be applied to other communities. First, we'll cover estimating bicycle and pedestrian exposure across the citywide network using existing count data that the City of Seattle has collected. We only used existing count data and counts were not conducted specifically for this analysis. And second, we'll go over a method used to optimize a count program to improve the quality of exposure data. A little background information, the BPSA was produced to advance Seattle's Vision Zero goals to eliminate fatal and serious injuries with a focus on vulnerable roadway users, such as people riding a bicycle and walking. The BPSA itself has several other components aimed at proactively and systematically addressing safety issues that included the development and application of safety performance functions, innovative and sophisticated video analysis, the development of rich graphics and visuals for effective public communication, and various crash analyses. So let's begin discussing exposure estimation and annualizing count data. The first step we took in developing citywide exposure estimates was working with permanent count data. We reviewed, cleaned, and validated count data from each permanent count location. Then we calculated hour of day, day of week, and month of year ratios for each location. Locations were then grouped by looking at patterns and volume distributions between each location. Then short duration counts from manual data collection, pneumatic tubes, or video counts that cover around a few hours or a few days were assigned to the permanent count location factor groups based on spatial proximity and land use context. The short duration count data was then translated into annual average daily volumes for pedestrians and bicyclists. The output of this is the dependent variables for the exposure estimation models. As mentioned in the previous slide, permanent count data from the available locations were translated into a standard format, cleaned, and were assigned factor groups by looking at volume peaks and distributions. The image to the right shows an example of hour of day factor groups. These count factors allow us to approximate average annual volumes while, in a way, controlling for the cyclical daily, weekly, and seasonal patterns that can affect the short duration counts observed at a given location depending on when the data was collected. So, for example, these methods allow counts taken during the winter to be used to estimate year-round averages without having the final result in a way penalized by the fact that cycling and walking activity is typically lower during the winter than other seasons. We then identified count locations around the city with similar temporal traffic patterns and evaluated the context to help in generalizing how these factors can be applied to short duration count locations. Based on our understanding of the city and the temporal traffic patterns identified during the factor estimation analysis, we created zones within the city to which we could apply each of the factor groups patterns based on spatial proximity, land use, and topographic characteristics. We executed this operation by digitizing using GIS to represent the zones and spatially joining to the short duration count locations with these polygons. While assigning the short duration count locations to groups, we sought to balance between assigning based on similarity of conditions and on spatial proximity. For count sites that are very close to a permanent counter, it's generally reasonable to assume that the patterns are similar. However, for locations that are a bit further from the counters, the factors had to be applied from different locations in the city to best match the likely underlying patterns. We then developed a set of spatial variables to relate to the count data using data provided by the City of Seattle and their very rich open data portal, and from other data sources such as census data, longitudinal employer household dynamics, which is employment numbers by sector, OpenStreetMap, and Strava. We used Strava data for bicycling exposure, but only as a predictor in the model, as we understand Strava's population of bicyclists is known to differ from the general population in some important ways. We also excluded Strava's pedestrian volumes because the majority of Strava's users are recreational runners and joggers, and that only represents a small portion of pedestrians and pedestrian trip types. We developed volume models for network segments for bicyclists and for crosswalks for pedestrians using negative binomial regression, which is a statistical technique built around estimating count variables. The purpose of this modeling exercise is fundamentally predictive. The goal is to develop equations that accurately estimate pedestrian and bicyclist volumes along segments and at crosswalks so that the City of Seattle can use these estimates to achieve other goals, such as assessing exposure risk and crash modeling. Major impetus for developing the BPSA Phase 2 was the availability of estimated motor vehicle volumes for the entire Seattle street network. This was developed by DataKind. The motor vehicle volume estimates allowed us to refine the Phase 1 exposure models and better assess crash risk. For pedestrian exposure estimates, the unit of analysis for pedestrians was not just at intersections, but was for each individual crossing of each leg at the intersection, so for each crosswalk, marked or unmarked. This approach is pretty novel in that it allowed us to estimate volumes based on major or minor legs at the intersection and use variables specific to each leg. The variables included in the exposure model, which is displayed in the graphic above, were selected using machine learning algorithms to identify variables that should be included or excluded from the final exposure model. After applying the pedestrian exposure model across the citywide network, every crossing and intersection on the network now has an estimate for the number of people walking at every crossing and at every intersection. The darker blue shades show high concentrations of estimated walking activity. The highest predicted pedestrian volumes are focused in the Central Business District near the University of Washington and the Neighborhood Business District, which fits with our general expectations of where pedestrians are most expected. After developing both bicycle and pedestrian network-wide exposure estimates, the next steps included developing states performance functions, or crash models, to identify the location characteristics most associated with pedestrian and bicycle crashes using machine learning and applying crash models to the network to identify locations that have the highest expected number of crashes at every intersection in the city, even if the crashes never occurred at that location. Essentially, we used statistics to link outcome variables such as the number of people walking or bicycling, and the number of crashes to a set of input variables such as roadway and land use characteristics. This process lets us then estimate the expected outcome or risk measured in the number of expected crashes based on input variables, even when there may not have been a crash yet to date. For both volume estimation and crash outcomes, we used a type of statistical analysis called negative binomial, which we discussed earlier, and random forest, which is a type of machine learning. We conducted the safety performance functions for 3 different bicycle crash types and 4 pedestrian crash types, like left hooks and right hooks. The results were the number of expected crashes at every intersection in the city. Now that we've discussed how count data is critical for understanding the travel patterns associated with active modes and in identifying priority locations for safety improvements through the development of safety performance functions. So how do you better understand active travel patterns in your community? One option is to develop a method that optimizes future data collection for bicycle and pedestrian volume data. In phase 2 of the BPSA, we developed a location prioritization algorithm to fill in gaps where volume data has not been collected, and the algorithm recommended future priority count locations based on key factors that we know have been identified as predictors of volume. Count locations should not be limited to where the highest level of activity are expected, but should reflect the variety of bicycle and pedestrian activity patterns across the entire city. Including both high and low activity count locations will create a more accurate portrait of bicycling and walking levels across your community. If only high count locations were fed into the exposure models, the volume predictions would not reflect the range of walking and bicycling levels and the variety of patterns found across the entire city, leading to less accurate estimation of crash risk across the city. More accurate volume and crash prediction estimates can be achieved by collecting counts from locations with the greatest variety of activity levels and location context. The goal of the location selection procedure detailed here is to improve representativeness of the count data sets across each of the variables identified in the current version of the volume models. Here, we alternate between considering bicycle count location prioritization variables and pedestrian count location variables. For locations with existing counts, the number of locations were calculated for each variable included in the model, such as population, employment, commercial land use, etc. The model then counts the number of locations for each variable that have no count data. If the number of these locations is less than 20 for each individual variable, then the location is given a score of 20 minutes minus the number of locations. Negative scores were assigned to nearby locations to discourage clustering. The location with the highest score is selected and added to the priority location list, and also added to the base list of locations of existing counts. This model is then repeated until the desired number of future count locations is identified. Here, with the BPSA Phase 2, we selected 80 locations to be prioritized for future counts to be conducted. This iterative and somewhat novel approach is designed to fill in gaps in the data collection scheme for factors that have been identified as predictors for volumes, while discouraging locating multiple counters in close proximity to one another. The process has been designed to be an iterative procedure to avoid simply placing all of the counts in a location that is currently a gap, but looks at what gaps will exist in the future as more counts are conducted. The output of this approach is a prioritized list that the city can use to make investment decisions for both permanent and short-duration counts. This will also lead to a more robust count program and more refined volume estimation and safety performance functions. So what have we learned from this work so far? We understand how a lack of volume of exposure data can be a barrier to robust safety analyses. Locations can be prioritized using algorithms and machine learning to expand count programs and exposure model inputs. And of course, these methods are not only applicable to Seattle, but they can be applied to any community. What are the next steps? What are the things that we're considering in the future? Well, evaluate the location prioritization algorithm performance and re-estimate models. and do some sensitivity testing to determine the number of future count locations to be prioritized to answer what the minimum coverage level might be. And with that, I wrap it up. Here's my contact information. Feel free to follow up with any questions, comments you might have. And for now, I'll pass it back to Kellyanne. Thank you.
Thank you, Brian. We will now move on to the question and answer portion of this webinar. I will now hand things off to Sarah O'Brien to go ahead and moderate.
Hi, everybody. Thank you so much for 3 really wonderful presentations. I definitely learned a lot and was taking notes myself. I see a few questions in the chat pod. Definitely feel free to enter those in if you still have some pondering questions so that we can ask them to the presenters. So one question that we have for Adul is looking at the information that you found on the near side versus far side bus stops. And a couple of folks were wondering why the crash frequency was more on the far side of the bus stops. That seemed a little non-intuitive. And so wondering a little bit more about why you think that may be, and if you specifically looked at how near side bus stops compared.
Thank you, Sarah. So most of the bus stops in Utah State is in lane. I know the far side bus stop is more recommended, but our model showed that the near side bus stop had less crash frequency. One reason for that may be when we place near side bus stop in lane, it enables simpler pedestrian access at crosswalk. It prohibits vehicles from entering opposing lanes to pass stop to transit vehicles. And if near side bus stops are placed close enough to the intersection, then right turning vehicles cannot merge in front of the stopped transit vehicles. That can be a reason. Yeah.
Thank you. Another question for you, Adul. Sean McNulty asks, it was noted that an increase in mean household size seems to greatly increase the frequency of pedestrian crashes. Did you have any potential explanations for why that might be?
Yeah, so mean household size, when it increases by 1 person, our model predicted that the pedestrian crashes will increase by 14%. So one potential reason for that may be that when mean household size increase by 1%, the overall population walking in the street increases, and that's why the number of crashes, the probability of crashes increases with the number of increased person. Yeah.
Thank you. Prasanna, one of the questions that came up for you is actually a question that I asked. You had mentioned the average silhouette width when you were talking about some of the information going into clustering. Can you explain what that is?
So thank you for the question. The average silhouette measures how similar the object is with its own cluster and how different it is from another clusters. We use the term separation and cohesion here. And the value of silhouette width ranges from -1 to 1, where high value indicates that the object is matched closely to its cluster and is separate from the neighboring clusters. So I used not only the average silhouette width, but other four cluster statistics to see how well it shows the efficiency of clustering. And that's why I was able to calculate the number of clusters seeing all those statistics, not only from the average silhouette width, but from all those statistics, seeing how well they match. and how efficient do they show the clustering?
Thank you. Another question for you, thinking about how the factor groups that you developed or the typologies that you came up with, the clustering, how do you think that those would transfer to the unsignalized intersections, those factor groups?
Yeah, this is a very interesting question. We haven't yet come up to that place where we are trying to transfer to the unsignalized intersections, but one of the things that we were trying to understand is how well the built-in environment characteristics can be associated with each typology. And once we are able to do that in a micro scale, then we can, let's say, transfer that, we can then transfer it to other intersections which has, where we can calculate those built environment characteristics and say that, so these intersections have this built environment characteristics, or this residential density, this much access to transit, then we can transfer it to our typology and then use those factor groups for our typology to that one.
Thank you. So thinking back for both of the Utah presentations, Adul and Prasanna, do you have a sense of what, how Utah DOT or maybe the local municipalities are ultimately going to use the pedestrian volumes that are estimated? You know, do you, the urban centers in Utah typically time signals to automatically give a pedestrian walk with each cycle, and therefore remove the need for actuation? And so how would you estimate pedestrian volumes there? Is it ultimately based on this idea of the built environment?
Sorry, I'm not sure about the question. Can you please repeat that?
Sure. So ultimately trying to understand what Utah DOT or local municipalities in Utah ultimately want to, how they want to use the pedestrian volumes that are estimated. And along the lines with Frank's question about transferring those factor groups to unsignalized intersections, there's also locations where you may have a signalized intersection where pedestrians always get the walk, and so there's no push button to collect that particular type of data in order to estimate the pedestrians crossing there. So thinking about how you might also need to estimate pedestrians in other intersection types that don't have actuated push buttons.
So there has been, we have been doing some analysis, not me, but our group, and Dr. Patrick have been doing that analysis where he had done calibration for those pedestrians which has a recall, that you don't need to press a button to get a pedestrian walk phase. And the calibrated models are quite different from those which have a recall versus those that doesn't have a recall. And I think the main idea behind UDOT was to, first of all, find those factors to convert those pedestrian push button estimates into actual volumes. Adul, you're free to answer now.
Yeah, so what UDOT is doing as of now, to convert the push button data in pedestrian volume, I heard they are also working, but I'm not sure what's the procedure they are following. Prasanna mentioned about some way. I'm not so sure about that. But for signalized intersection, they are converting the push button data in some useful form of pedestrian exposure. Yeah.
Okay, thank you. Brian, a question for you. For the count location prioritization algorithm, why was 20 used as the threshold?
For 20, well, we did 20 and 40, 20 for bikes and 20 for, or 40 for pedestrians. And that was just applying a negative score to nearby locations. And that was just to knock them down a bit so that we avoid clustering of planned or of recommended location. It's somewhat arbitrary, the number itself. We just wanted to get good coverage with the outputs. Does that answer your question?
I believe so. And another question for you. You had listed on the side, that same slide, you had a list of all the factors that were going into that, and you mentioned an equity score. Could you explain a little bit more about what that is or what that means for Seattle?
That's right. So that equity score was produced by the City of Seattle. It's a data set that was provided to us. And if I'm not mistaken, I can't speak to the specifics of how the equity score was actually produced. But if I'm not mistaken, I think it included race, number of cars available, people who identify as being disabled, and I'm not sure what other variables might have been included.
Okay, so that was data that came from Seattle.
That's right.
The city. Okay. And another question for you, how did you calibrate the pedestrian volumes?
If I understand the question correctly, we adjusted the short duration counts to produce annual average daily pedestrian traffic volumes following the factor process that I had touched on. We then developed a predictive model using negative binomial regression, and that produced the pedestrian volumes.
Okay, thank you. A follow-up question to you. When you developed the exposure models for Seattle, did you develop those by different intersection types?
We built out the locations from every intersection, but we didn't necessarily break them out by different intersection types. We did, however, use variables that were specific to each intersection and each leg of the intersection in the models, though.
Thank you. Back to Adul, one of the audience members thought that it was surprising that weather and lighting was not significant in your model. Do you have any idea why that may be?
Yeah, thanks for the question. So Utah's weather, in Utah, the winter exists for like most of the time of the year. So one reason for that may be that during winter, the public, the people don't use the crosswalk that much. Yeah, and for lighting, most of the Utah streets are well lighted. We